Welcome to this lecture where we are talking about transactions, opcodes, and gas. At the end of this lecture, you will have a better understanding of the gas requirements for interacting with the Ethereum blockchain. The first big misconception is that reading operations doesn't cost any gas. I've heard things such as it's just a call, it's not a transaction. Well, a call and a transaction are both transactions and they both cost gas during execution. The difference is that a call doesn't have to be mined by a miner in the network because it doesn't change anything on the blockchain. So effectively, you mine the transaction for the call yourself. That way, you're paying yourself the gas fee, which is a zero-sum game. But even a call can run out of gas. So also for reading operations, it is important to understand the gas requirements of the executed function. So every single operation costs gas on the Ethereum blockchain. The amount of gas it costs depends on the opcode it executes. Here you see a screenshot of the Ethereum yellow paper, Appendix G. In this part of the yellow paper, the gas cost for specific groups of operations is defined. For example, the first few groups. G base costs 2 gas, G very low costs 3, G low costs 5, G mid costs 8, and so on. But what are the opcodes defined in these groups? You can also find it in the yellow paper. For example, the opcode stop, return, or revert costs 0 gas. Address, caller, or pop costs 2 gas. Add, sub, and so on costs 3 gas. Jump I would be in the group W high and cost 10 gas. I will go back to Remix again and show you exactly how the gas is calculated. This way you get a better understanding of what's happening under the hood. In the following example, we are running a few experiments. First, I want to show you the gas for the transaction, how it's calculated. Then I want to show you that also a view or a pure function can run out of gas. And at the end, we will conclude that it's a bad idea to run loops in general and why we always have to keep an eye on the performance of the code. I'm here again in Remix, and in this lecture we are using the exact same contract from the previous example, example 2, and you can find this file also in the course repository as ex2.sol for Solidity. In this lecture I'm going to show you how the gas is calculated, and we're running a simple example. We are just interacting with this function. And this function is a read-only function, but you will see that it also consumes gas. Now, I would say let's head over and create the contract. So we have the contract instance now, and we can interact with it. Let's calculate the sum of 3 and 4. Well, it should be 7, and it is 7. Let's drill into the details. You see that there is an execution cost and a transaction cost. Because it's a pure function, it says cost only applies when called by a contract, but we will see in a second that you can also trigger an out of gas exception with a view function. First, have a look how the transaction and the execution cost is calculated. When we hit the debug button, then we can again drill into the execution. And with the step-by-step debugger, we can see the exact opcodes that are executed. Now, each opcode has a specific amount of gas it consumes, and how much it consumes can be seen in the yellow paper and also in this very handy Excel sheet that I'm going to show you now. And you see that the total execution cost of the contract that we were running in Remix is the sum of all the used gas for each opcode. Actually pretty easy and straightforward. Now, the transaction cost in Remix is actually the transaction cost plus the execution cost. On the Ethereum blockchain, for each transaction, you also pay gas. That is independent from any opcodes that are running. From the Ethereum yellow paper, you can see that for the arguments that are sending in the transaction and the return values and the transaction itself, you pay gas to the miner. Okay, so now you know how gas is calculated. Let's run an experiment. Let's try and create an out-of-gas exception with a constant view function. Let's change our example to a bit. The logic that we change it to in this example is completely useless. It doesn't do anything useful. But it should just show you that even with a comparatively small for loop, you can run easily into out-of-gas exceptions. So now we have two functions. One is a real transaction and one is just a view function. Both are having loops and assigning the balance of the contract to a variable. That costs gas because according to the yellow paper, getting the balance costs a certain amount of gas. Now let's see what happens when we run the function with a transaction. As you can see, we're running out of gas. There's an out of gas exception. Now, what happens if we're running the function that actually just a call, the view function? Surprise, same thing, out of gas exception. So if you ask me for the takeaway from this lecture, understand that every single instruction uses gas and try to avoid loops. You can use loops if you can really estimate the gas that's being used up during execution of the smart contract.